Hello, welcome to the class. We are studying about heterocyclic compounds. So far in the class, we studied about compounds pyrrole, furan, thiophene, pyrazole, imidazole, oxazole, and thiazole. In today's class, we will study about pyridine. You know, benzene is a very popular and very important chemical in organic chemistry. In a similar way, pyridine is a very important and very popular chemical in heterocyclic chemistry. It is also important in the examination point of view. Let's study about pyridine now. So as you can see on the screen, pyridine is a six-membered heterocyclic compound with one heteroatom, that is nitrogen. So far we studied five-membered heterocyclic compound with one or two heteroatoms. So today we are going one step ahead and studying about a six-membered heterocyclic compound. Here it is pyridine with one heteroatom, that is nitrogen. Pyridine occurs along with the pyrrole in bone oil and the light oil fraction of coal tar. We studied about this in pyrrole, right? So pyridine ring is highly distributed in nature, and pyridine also present in medicinals. So we are going to study about these in the later part. Next, we will go to the structure. We will look at the structure in detail. As you know, pyridine is a six-membered heterocyclic compound. It has got five carbon and one nitrogen. And all these carbon and nitrogen atoms, they are sp2 hybridized. Carbon has got six atomic number, means six electrons. So in the outer principal level, it has got four electrons, and that is getting distributed among three of the sp2 orbitals and one p orbital, one empty p orbitals or unshared p orbitals, right? In a similar way, nitrogen is also sp2 hybridized orbital. It has got one more electron than the carbon, so one more electron is going to go with the sp2 hybridized orbital. So there will be one extra electron in one of the sp2 orbitals. So all these sp2 orbitals, they will form the, as you can see here, let me bring up the pen here. So all of those sp2 orbitals, right, all of those sp2 orbitals of this is one, this is one, these are all sp2 orbital bonds, right? Again there is one sp2 here, one sp2 here, here one more sp2. It forms bond with the s orbital of hydrogen. So right, then the nitrogen will have two electrons in the sp2 hybridized orbital. So nitrogen, again the unhybridized p orbital is going to have one electron in each of carbon and nitrogen. So each carbon will have one electron. So as you can see here, your nitrogen will have one unhybridized p orbital. Now what is going to happen? It has got six electrons, and there will be formation of three pi electrons, and these pi electrons are delocalized, so they are going to form the cloud. As you can see here, they are going to form the cloud. So this pyridine molecule is In a ring form, it is flat, it's planar, it has got delocalized electrons, and there are 6 electrons. It will fulfill the Huckel rule where n is equals to 1. So pyridine is a aromatic compound. Alright, this is the resonance structure of pyridine. At a given time, pyridine can exist in these different forms. So you're going to you're going to write this resonance structure by shifting of the bonds. These because the pi electrons are delocalized, so you just have to move the electron from one atom to the another atom, and you can see the different charges on carbon and hydrogen. So these are the resonance forms, right? Now there is a frequent examination question, which is stronger, pyridine or a pyrrole. So it says pyridine is stronger than pyrrole. We need to know the reason why pyridine is stronger than pyrrole. Now stronger base than pyrrole. So what is a base? So base is the substance which can give pair of electrons. Now between pyridine and pyrrole, this is a pyridine structure, and this is a pyrrole structure. Between these two, which one is ready to give the electrons, or which one has got more electrons? As you can see here, these the two electrons from the unhybridized p orbital from the pyrrole, that is in the ring, that is in that electron cloud, the pi orbital ring. Okay, it is strongly bound there. So there is a similar situation here, right? But there is only one electron for this this ring from the nitrogen, but there are two free electrons in the nitrogen from sp2 hybridized orbitals. So these electrons from sp2 hybridized orbitals, they are ready to give out the electrons, and because of this free two sp2 hybridized orbital electrons, your pyridine is more stronger than the pyrrole, so it can give the electrons readily. So that is what is the nature of the base. That's why pyridine is stronger base than pyrrole, and this structure is the which it tells the pyridine is aromatic. The free electron cloud is represented by the circle at the center of the pyridine structure, and two electrons are the two dots here. These are free electrons from the sp2 hybridized orbitals. Alright, let's go to the synthesis. The first method of synthesis is from acetylene and hydrogen cyanide. As you can see here, this is one acetylene, right? This is another acetylene with the three bonds, right? With three carbon bonds, and this is, so you're taking two molecules of acetylene and one molecule of hydrogen cyanide. So this is your hydrogen cyanide. So combination of these, mixture of these is passed through red hot tube. So you are going to get pyridine as the product, right? This is the first method of synthesis. The second method of synthesis is from piperidine. Piperidine, what is piperidine? It is a hydrogenated product of pyridine. It's a saturated product of pyridine actually. So if you get piperidine at a lesser cost than the pyridine, so you can prepare pyridine from piperidine, right? So what you have to do, because it is a saturated or hydrogenated product, you have to dehydrogenate it. So dehydrogenation is done at 300 degree centigrade with the concentrated sulfuric acid. So you are going to get pyridine as the product. So instead of concentrated sulfuric acid, you can use nitrobenzene. You can use nitrobenzene instead of concentrated sulfuric acid to get the pyridine from pyridine. So this is second method of synthesis. Third method of synthesis is from pyrrole. So pyrrole, what you have to do, you have to heat pyrrole with the dichloromethane. So this is dichloromethane. You have to heat pyrrole with dichloromethane and sodium ethoxide. This is sodium and this is your ethoxide. With the sodium ethoxide, so you are going to get pyridine as the product. So you are going to get ethanol and sodium chlorides. They are the byproducts here. So this is the third method of pyridine synthesis from iron. The fourth method of synthesis is from acetylene and ammonia, and you have to take formaldehyde dimethyl acetate. What is this formaldehyde dimethyl acetate? So see, this is aldehyde and this is acetal. If you react ethyl or the alkyl ethanol or alkyl alcohol, right? Alkyl alcohol. So you're going to, and if you react that with the aldehyde, you are going to get acetal. You're going to get acetal with the two OR groups. A similar product is taken here. Name of the product is formaldehyde dimethyl acetal. Formaldehyde dimethyl acetal. So it is taken along with the acetylene and ammonia. This is your acetylene with the three bonds between carbon and carbon to acetylene molecule, and you're going to take ammonia, right? Then you are going to take formaldehyde dimethyl acetal. So you're going to subject this along with the aluminum oxide at 500 degrees centigrade. So you're going to heat them to 500 degree centigrade. So you're going to get the pyridine as the product. So this is the fourth method of synthesis. Next, we'll look about the properties of pyridine. First one is physical properties. It's a colorless liquid with a boiling point 115 degrees centigrade. It has got very characteristic pungent and disgusting odor. You have come across pyridine in the laboratory. I have seen the disgusting, you are very reluctant to take the odor, and I'm very sure you know about a pyridine that we used in the laboratory. So it's miscible with the water, it's soluble in water, and most of the organic solvents like chloroform, ethanol, and ether. So chemical properties, it's basic in nature, like we already discussed in comparing pyridine with the pyrrole, right? So pyridine is has got basic character, so it's a base. It behaves as a base. It has got pKb of 8.7. Let's compare that with the ammonia. So ammonia has got pKb 4.75. As it says here, as the pKb decreases, the product is a strong base. So our pyridine has got pKb of 8.7. That means pyridine is weaker base than ammonia. Ammonia is 4.75 and pyridine is 8.7. So pyridine is a weaker base than ammonia. And pyridine reacts as an acid. It reacts, as a base. It reacts with the acid and it gives the stable salt. So pyridine reacts with the hydrochloric acid and it's giving here pyridinium chloride. So it is pyridinium chloride. So it's it's a protonated product. The hydrogen is the proton is going to join with the nitrogen there, right? It's a protonated product. And let's see about the chemical reactions of pyridine. The first one is electrophilic substitution reaction. It is not going to give the electrophilic substitution reaction easily, and if you try to carry out the reaction with the electrophiles, this is what the product you get. This is not the substitution reaction. The electrophile is going to attack at nitrogen. So if it is a substitution reaction, it is supposed to be on one of these carbons, right? It has to replace the hydrogen, but that is not going to happen here. But in vigorous condition, electrophilic substitution reactions are going to happen, and the substitutions are going to take place at C3, at carbon 3. Where is the carbon 3? This is 1, position 1, this is position 2, this is 3, and this is 4, right? This is 5, and this is 6. Right, the substitution is going to take place at carbon number 3. Now we will see why is substitution going to take place at carbon 3. Why not at carbon 2 or carbon 4? The similar ones are like C5 and the similar ones are at 6. So it is not the substitution reaction is not going to take place at carbon 2 or carbon 4. It is going to take place at carbon 3. Let us see why is that. These are resonance stabilized structures of pyridine. Right, these are the intermediary stages. We have to look at these products here. Um, what we are going to do here is we are going to draw the resonance structure at each of the carbon, that is at C3, C2 and C4, and after drawing these structures we are going to see which structure can be more stable, which structure can exist, which structure can happen so that the product can be formed. Alright, let's look at C3 attack. C3 attack. So this is the electrophile has attacked at C3 here, right? So here is the attachment of electrophile. Then there will be changes um, in the charges in the pyridine, right? When electrophile gets attacked over here, this bond, this pi bond electron are going to shift for the electrophile, right? Those electrophile attachment bond needs the electron, right? It needs 2 electrons for the formation of the bond. So the bond from here, or the electrons from here, are going to shift here. That's why there will be positive charge over here. Like this, you have to consider shifting the electrons, and by that, for C3 attack, so you are going to get one positive charge here, one more positive charge here, and one more positive charge over here. So you're going to get 3 different resonance structures. Okay. Now let's go to the C2 attack. C2 attack. What will happen when it is attacked at C2? So you're going to get one positive charge over here, one more here, and one more here. Now what will happen when there is positive charge on the nitrogen, and there is positive charge on the nitrogen at this stage, right, on this resonance structure, but nitrogen is electronegative atom, so it is going to attract the electrons. So this structure, the structure A written here, it is not that stable. This is not going to happen, we can say. So it is going to these two structures can be formed, but this structure is least likely going to form. A similar one is here at attack at C4 position. You are going to get one resonance structure with the uh, positive charge on the nitrogen. Even this is not going to happen. These two so attacks at C2 and C4 resonance structures are least stable. Not They are not going to happen. That's why the attack will take place at C3. C3 attack is more stable. That's why the electrophile is going to attack at the C3 position on pyridine, not at C2 and C4. So these are the examples of nitration. So nitration, how you are going to carry it out. So you're going to take potassium nitrate in the presence of sulfuric acid. So you are supposed to heat the reaction. The substitution is going to take place at position 1, at position 3, right? So you are going to get 3 nitropyridine. So you have to heat the reaction at 300 degree centigrade, as I told you. So electrophilic substitution reactions are going to take place in a vigorous vigorous reaction condition. Next is the sulfonation. You have to carry out this reaction at 230 degrees centigrade, high heat reaction. The pyridine is going to react with the fuming sulfuric acid. Fuming sulfuric acid is nothing but oleum. Fuming sulfuric acid in the presence of mercury sulfate, and the heat is the temperature is supposed to get to 230 degrees centigrade. You are going to get three substitution product, that is pyridine 3 sulfonic acid. So this is the product you are going to get. That is about sulfonation. Next is bromination. You are supposed to carry out this reaction at 300 degrees centigrade. Okay, but you are going to get a polysubstituted product here. Pyridine or bromine gas and pyridine, they both, you are supposed to pass on charcoal, right? You're supposed to pass on charcoal at 300 degrees centigrade. You're going to get a 3 bromopyridine, one product, and a 3,5-dibromopyridine, that's the another product. Friedel-Crafts acylation and alkylation. Friedel-Crafts acylation and alkylation are not going to take place. So as you can see here, this is the Lewis acid or aluminum trichloride. Lewis acids are actually electrophiles. So this is it is actually not going to substitute here or here anywhere on the ring. So it is going to attack here on the nitrogen. Attack is going to take place on the nitrogen, not at the carbon. So it is not a substitution reaction. So that's why it says the Friedel-Crafts acylation or alkylation is not going to take place for pyridine. So a different product is going to form. So the product is a pyridine aluminum complex along with the aluminum trichloride. So that is about Friedel-Crafts acylation and alkylation. So next is nucleophilic substitution reaction. The question is where is the nucleophilic substitution is going to take place. So it is going to occur at C2. It is going to occur at C2 or C4. So it is going to occur at C2 or C4 instead of C3. So in case of electrophilic substitution reaction, the substitution was going to take place at C3, but in this case, in nucleophilic substitution reaction, substitution is going to take place at C2 or C4. So for that, to give the reason why it is taking place at C2 or C4 instead of C3. So we will have to write the resonance structures. As we here the resonance structures are written. This is at C2 position, and these are resonance structures at C4, and these are resonance structures at C3. Let's look at the um, intermediary stages. So you're going to have negative charge on the nitrogen. Negative charge on the nitrogen is more stable. So here, so you're going to get one resonance structure in out of these three structures, negative charge on the nitrogen. Here again, one more negative charge on the nitrogen. So you're going to get this here. So in the attack at C3 position, you are not going to get a negative charge on the nitrogen. So we can say this is least stable. There is no negative charge at the nitrogen. So this attack at C3 is at least stable. The attack at C2 and C4 is more stable. That's why attack is going to take place at C2 or C3. Alright, these are the examples. The first example is a reaction with the sodamide. Right, this is the nucleophile sodamide, sodium NH2. Okay, it can, the sodium is positively charged and NH2 is negatively charged. So this is the electrophile. So it is going to attack where at the C2 position. Right, it's going to attack here. Now the because the of the electronegativity of the nitrogen, this is going to be like more positive, and this is going to, the ring is going to be more positive, and the electrons will be towards this nitrogen. That's why this the nucleophile is going to get attracted towards the ring, and it is going to attack at C2 position in the presence of liquid ammonia and heat. So you are going to get 2 amino pyridine as the product for the reaction with the sodamide. So you have to carry out the reaction at 100 degree centigrade. So what is the mechanism? Just now I explained this. So you are going to get the nucleophile. Of course, the first the attack will be on here, and with that you are going to get the attack from the sodium on this negatively charged nitrogen on the pyridine ring, and that is again this is going to get discharged. This is going to react with the hydrogen from here, right? Sodium hydride you are going to get, and sodium hydride, and this ammonia is they are going to react, and you are going to get back the sodamide acting as a catalyst here. All right, now next is the reaction with the sodium hydroxide nucleophilic reaction. You have to carry out this reaction at 300 degree centigrade, and the reaction to be done in the presence of oxygen, and you are going to get 2-hydroxypyridine. It is also called as pyridol, and 2-pyridone product. 2-hydroxypyridine and 2-pyridone. So you are going to get the keto substitution over here at C2. Next is the reaction with the N-butyl lithium. So you have to carry out this reaction at 100 degree centigrade. As you can see here, N-lithium butyl lithium. This is butyl group. So this is lithium. Lithium will get partially positively charged. So the butyl chain is going to get partially negatively charged. So because of that, so it is going to attack over here at C2 position, and you are going to get a 2n-butyl pyridine as the product. So that's about nucleophilic substitution reaction. Next is oxidation. It says oxidation is quite stable to mild oxidizing agents. It also does not react with the chromic acid or nitric acid, but it reacts with the per-acetic acid. It reacts with the per-acetic acid. This is per-acetic acid. Structure is similar to acetic acid with one extra oxygen, which you can see here. With one extra oxygen, it is per-acetic acid. It is a good oxidizing agent, and pyridine is going to get converted to pyridine and oxide. So substitution at nitrogen of a pyridine, the product is pyridine and oxide or pyridine 1 oxide. Next is the reduction using hydrogen in the presence of nickel as a catalyst at 200 degrees centigrade. So you are going to subject it for hydrogenation. You are going to do the saturation of the pyridine ring. You are going to get pyridine. We have seen in the synthesis of pyridine the reverse. We have seen the reverse reaction of this. So instead of nickel, so you can use nickel and hydrogen. So you can use lithium aluminum hydride to do the hydrogenation, right? So this is about the reduction. And next is a reaction with the alkyl halide. Alkyl halide, it is going to um, attack on this nitrogen of pyridine. So you're going to get with the methyl bromide. So you're going to get N-methyl pyridinium bromide, N-methyl pyridinium bromide, or it is also called as the 1-methyl pyridinium bromide. So those are about the reactions. So let's look at the uses of pyridine. Alright, pyridine is used. I have distinguished them into like general uses, then the biological uses and medicinal uses. Okay, or the importance of pyridine. So under the uses, it is used as a basic solvent. As I have told you, it is very important and very popular chemical in heterocyclic chemistry. It is widely used as a basic solvent. It's a basic compound. Also, it is used as a solvent, as a liquid in the reaction. Right? It is not just as the medium for the reactions. It is also used as a reactant in the reaction. It is also used as a catalyst in the reaction. Right? It is widely used, and it is used to denature the ethyl alcohol. Ethyl alcohol is your regular alcohol. It is used to denature alcohol. What do you mean by denaturing the alcohol? Alcohol can be misused easily. Alcohol is used for the consumption purpose as well as for other purpose, like in the industries, in the laboratories, like for other preparations, like for sanitizers, you need alcohols. What if these the alcohols which are used for the other purposes are used for consumption purpose? So that means it can be misused, right? To prevent the misuse of the ethyl alcohol, it is been denatured. The actual nature of the alcohol is been removed. To denature this, they add pyridine. They add pyridine in the alcohol. So the pyridine, what it does is it like we came across, it has got the disgusting odor, right? To give that disgusting odor, so pyridine is added to the ethyl alcohol so that nobody can consume this. Apart from giving disgusting odor, so it can cause a stomach upset or it can cause harmful effect. That's why because of this nature, people are not going to misuse the industrial alcohol or laboratory alcohol. So other than pyridine, they also use ethyl alcohol to denature the. Other than pyridine, they also use methyl alcohol to denature the ethyl alcohol. So that's the general uses of pyridine. Let's look at the importance of pyridine in the biological system, or importance that is available in the nature. Pyridine derivatives occur biologically and in nature, right? Niacin, niacin is vitamin B3, right? It's a combination of nicotinic acid and nicotinamide. Combination of nicotinic acid and nicotinamide is called niacin, and niacin is nothing but vitamin B3, and niacin will help us in a digestive process. It is also good for skin. The deficiency of niacin can cause the disease called pellagra. It can cause the skin disease called pellagra. So niacin is very important compound, right? It's also a vitamin. So study of this niacin or niacin related compound is very important. Then NAD and NADP, I'm sure you have come across this in the anatomy physiology chapter or in the biochemistry. So NAD, nicotinamide adenine dinucleotide, NADP, nicotinamide adenine dinucleotide phosphate, these are coenzymes. These will have the pyridine structure, right? The pyridine ring is present in these structures, and this coenzyme will help us in oxidation reduction reaction inside our body. So they act the pyridine derivative as NAD and NADP can act as coenzyme, and this will help us in oxidation reduction reaction inside our body. Then pyridoxine is a pyridine derivative. Pyridoxine is nothing but vitamin B6. Vitamin B6 will help us to make the hormones like noradrenaline, serotonin, and melatonin. So these are the three hormones. Those can be prepared inside our body using pyridine derivative, that is pyridoxine or vitamin B6. The pyridine also occurs in nature as an alkaloid called nicotine. Nicotine is that is used in the cigarette, right? Tobacco. Nicotine is a tobacco product, and nicotine is also used to for weaning from cigarettes, right? Nicotine product, nicotine gums or nicotine chewing gums are there. Here the depending on the how many cigarettes the person takes, the dosage of nicotine or nicotine patches or nicotine gums, dosage of these are tuned. And gradually they reduce the dosage of nicotine in these gums or patches, nicotine patches. So this will help in abstaining from tobacco products. So that is the use of nicotine as a medicine actually. So next is using pyridine derivatives in medicinals. I mean, these are the artificial products. Nicotine is the natural product, so these are the artificial products or the products those are synthesized in the laboratory for medicinal purpose. The first one is nicotinamide. So it's Coramine is the popular brand. Now this brand does not exist, but it is well known as the brand Coramine, right? It is nicotinamide is used as a cardiac and respiratory stimulant. So, respiratory stimulant in case of breathlessness, where the oxygen is needed, or also in case of poisoning of carbon monoxide, it's used as a respiratory stimulant. It's also used as a cardiac stimulant as well as a circulatory stimulant, or in cases of a circulatory failure, it can be used. So it is also used in shock. So these are the uses of nicotinamide. Nicotinamide is a derivative of pyridine. As you can see here, pyridine ring, right? This is the structure of nicotinamide. Right, next is isoniazid. Isoniazid used in the treatment of tuberculosis. This is the isoniazid structure. You can see the pyridine ring here. So this product is used in tuberculosis or TB. So next is sulfapyridine or sulfasalazine. These are sulfa products. These are sulfa products. So these are antibacterials, right? These products are used in dermatitis. These products are used in dermatitis, and sulfasalazine is used in ulcerative colitis. So this has got a pyridine ring, as you can see here. This is the structure of sulfapyridine. This is the structure of sulfapyridine. So sulfapyridine and sulfasalazine are sulfa products or sulfonamide products. So next is omeprazole, lansoprazole, pantoprazole, rabeprazole. So these are the proton pump inhibitors. These will have pyridine ring in them. Proton pump inhibitors are used in case of ulcers. They are used in ulcer. There are many types of ulcers, right? So that they are like GERD, gastroesophageal regurgitation disease, GERD, 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 a type of ulcer. Then you have peptic ulcer, you have duodenal ulcer, right? You can use omeprazole, lansoprazole, pantoprazole, and rabeprazole in these diseases, ulcerative diseases. So this is about pyridine. We studied occurrence of pyridine, right? We studied the structure of pyridine. We studied the properties of pyridine. In that we studied the physical property, chemical property. Then we studied the uses of pyridine. So this finishes about the pyridine, and thank you very much, and let me know if you have any questions.